You'll have access to this later. So there it is. I am recording the lesson at this point. The section is 10.5. We are skipping 10.4. So don't worry about 10.4. And the objective is to use Pascal's triangle to break apart binomials to what we call create a binomial expansion. So first, let's define what a binomial is. A binomial is a two terms added or subtracted together. That's it. So if you look at the example here, x plus y, x plus y, x plus y, right? So if you are asked to raise in the first one, for example, x plus y to the 0 power, well, anything to the 0 power is 1. So therefore, that one simplifies just neatly to 1 with no issue. The second one, x plus y to the first power. Well, you're not raising it to anything but 1, so it's just x plus y, no change. The third one is technically x plus y times x plus y. And you would FOIL that. I don't think anybody has any trouble there. You get x squared plus xy plus xy plus y squared, which of course simplifies to x squared plus 2xy plus y squared. I'm going to have to write a little smaller for this last one here. But if I expand the third one, it is x plus y times x plus y times x plus y. Well, we already know that when you multiply two of them, you get this, right? So this is really, x squared plus 2xy plus y squared multiplied by another x plus y factor, right? Two of them when multiplied gives me this, and I'm multiplying by a third one here. So if I expand that and I FOIL this whole thing out, well, not FOIL, but distribute, I'm going to multiply everything by x, and I'm going to multiply everything by x, or by y. So if I multiply by x, I get x cubed plus 2x squared y plus xy squared. And if I multiply by y, I get x squared y plus 2xy squared plus y cubed. Probably fit that y cubed in there. Plus y cubed. And so that simplifies to, if I piece together the parts that are alike, I've got 2xy or 2x squared y there, and I've got another x squared y there. And then I've got xy squared and 2xy squared. So the ones that I've highlighted are of like terms, so I can put them together and kind of simplify this thing. X cubed plus 3, 2 plus 1, again, 2 of them plus another 1 of them, plus 3 x squared y's plus 3 xy squareds. If you look at the blue ones, xy squared and 2xy squared makes 3 of them, plus y cubed. All right, so x plus y cubed, when you take that binomial and you raise it to the third power and expand it, you end up with this. Any questions with what I've done so far? I'm just kind of rigorously expanding each of these binomial expressions. Questions at all? Comments at all?
No.
Everybody's good with that? Okay. The objective here, the reason why I'm doing this, is we want to look at a pattern. We want to try to figure out what happens. What would happen if I did x plus y to the 4th power? What would happen if I did x plus y to the 5th power? Obviously, it's going to get bigger and bigger and bigger, but there are some patterns that you can recognize just by going through the 0 to 0 power, the 1st power, the 2nd power, and the 3rd power. The patterns are outlined here in 1 through 4 observations. First, in each expression, there's one more term than the power. So if the power was 0, we had one term. It happened to be 1. If the power was 1, we had 2 terms, x and y. If the power was 2, we had 3 terms, 1 term, 2 term, 3 terms in the answer. If the power was 3, we have 1, 2, 3, 4 terms in the answer. So there's always one more term than the power. That's the first observation. The second observation, this is pretty critical. Notice how the exponents increase for y for the second term, but decrease for the first term. So if we look at the last one here, the x started with the highest power, started with the cube, and then for the second term it went to a square, and for the third term it went to x to the first, and for the fourth term it's gone because it's x to the 0. So the exponent on the x, the exponent on this first term was 3, 2, 1, 0. The first term's exponents decrease in power. The second term in your binomial, which is y, increase. They start at 0. Technically here it's y to the 0, and then it goes y to the first, y to the second, y to the third. That pattern is always true. You can look at the one above it. Starts at x squared, goes to x to the first, and then it's x 0. And then the y is y to the 0, y to the first, y to the second. So they alternate. One of them increases while the other one decreases. That's observation number 2. Does that make sense to everyone? Any questions about that? We're good? The third says the sum of the powers in each term should equal n. So if you were to add up the exponents in each individual term, it should equal the highest power here, n. All right, we're talking about x plus y to the n power. So if it's the third, notice here, the exponent is 3. Here, 2 plus 1. 2 plus 1 is 3. 1 plus 2 is 3. And then this one is just 3. So that every term should have exponent 3 on the variables when you add them up. That's an easy one to see. And then finally, it's the coefficients. We are going to spend a lot of time. These notes are really talking about, more than anything, the coefficients. The coefficients will increase and then decrease in a symmetric pattern. That pattern you can see easier, I think, when you're looking at the whole Pascal's triangle. That pattern, again, starts at 1, goes up to a value, and then will decrease back down to 1, always. When we say coefficients, we're talking about the numbers in front of the variables. It's the number attached to the front of the term. And if you look here, it's 1, 3, 3, 1. Starts at 1, goes up to 3, and then decreases back to 1. All right. Let me confirm here real quick with this text that they're trying to give me. Hold on one second. Apparently John is about to join us, I'm hoping. Not with us yet, but he says he's going to be. All right, everybody with me so far? Any questions on what I've shown? Okay. Pascal's triangle is how we find these coefficients. All right. Our job in this lesson is going to be about applying Pascal's triangle, which you can see now almost being built. These are not quite fond of the way this is presented, but I guess it works. Pascal's triangle is a simple listing of what the coefficient factors are when you raise, for instance, if this was x plus y to the 0 power. When it says row 0, that's x plus y to the 0. And this is row 1, that's x plus y to the first power. And this would be x plus y squared, and so on, x plus y cubed. All right, so if I had to expand x plus y to the 0, then I know that the coefficient is going to be 1. If I had to expand x plus y to the first, I know the coefficients are going to be 1, 1. If I go back up and look, coefficients 1, 1, right? Go down to this one, x plus y to the third. The coefficient should be 1, 3, 3, 1. 1, 3, 3, 1. It's plain as day. It is exactly the way that that it showed, that it turned out. This triangle is mimicking the way it turned out in our expansion that we did by hand. All right, all good? So how do we find the next row? You kind of, these are supposed to be underlines. So this should be 1 underlined, 3 underlined. To find the next values, there are always ones in the far left and far right positions, always ones. All right. To find the values in between, you add the previous two right above it. So 3 plus 1 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And notice, like observation number 4, if it was x plus y to the 4th power, if we were trying to expand x plus y to the 4th power, the coefficients would be 1, 4, 6, 4, 1. They would increase and then decrease in a symmetric pattern. And then the next row would be 1, 5. If I add the two values immediately above it, 1, 5, 10, 10, 5, 1. And then 1, 6, 15, 20, 15, 6, and 1 if I was taking x plus y to the 6th power. And x plus y to the 7th power, I'm going to keep going. X plus y to the 7th power would be 1, 7, 21, 35, 35, 21, 7, 1. And so on and so on. I'm not going to keep writing it. This triangle is shown in a actually a pretty nice, succinct way, I think, on the next page. So here we go. It says, surprise, Pascal noticed that the numbers in this triangle are precisely the same numbers that are the coefficients of binomial expansions. Can you guys see this okay with the blue?
Yeah.
So x
Yeah.
plus y to the 7th, 1, 7, 21, 35, 35, 21, 7, and 1. Again, notice all the patterns, all 4 observations that we just talked about. The x's start with the highest power, 7, and then decrease down to x to the 0. So they start at 7 and then go 6, 5, 4, 3, 2, x to the 1, and then this is technically x to the 0. There is no x there. The y's start at y to the 0 in the first term and then increase slowly. Y to the 0, 1, 2, 3, 4, 5, 6, and 7. If we had to expand x plus y. Right now, patterns are clear. Hopefully you can see them. These 4 observations are listed again in the notes. You can go back and review them and look at them and have them on hand. It's not a bad idea also to have Pascal's triangle sitting somewhere where you can access it, or just Google it, for crying out loud. Google any, just a Google search, Pascal's triangle, and you can pull up a full version, probably to the 19th expansion, x plus y to the 19th power if you wanted to. All right. Our job is to be able to take expansions that are a little more complicated, not x plus y, that's easy, right? Those are just straightforward as can be. But what if I change it? What if I do 2x? And what if it's not y, but 3? So if it was 2x instead of x, then you'd have to imagine that up here in this general basic pattern I've got, anywhere there was an x instead has to be 2x. And so therefore 2x to the, for example, the 7th power, I'd have to take 2 to the 7th power and x to the 7th power in this spot. And then that would have to be true about everywhere there's an x all the way across this thing. And then instead of y, I have 3. So everywhere there's a y, I'd have a 3. So this term, let's say it was to the 7th power. This term right here, that y is now a 3, and that x is now a 2x, right? So I'd have to multiply 2 to the 6th and 3 times this number 7. So it's not going to be a number 7 in front anymore. It's going to change into something much bigger. If you change from x and y, you're going to change the coefficient. all right? But these factors are still there. They're still in the problem. So our job is to expand binomials. So number one, it says, use Pascal's triangle to expand the following binomial. I'm not going to ask you to take one and expand it all the way to like the 7th or the 8th or the 19th power or something. But what I might do is I might say, tell me what the coefficient is, the number in front, coefficient. Tell me what the number in front is on the 2x plus 3 to the 15th power. What's the coefficient of the x to the 13th power? And you would have to go through and find just the number in front. That's what we're about to practice. All right, so my best advice, create a table. Table should have 3 columns or 3 rows. 1 row for the values from Pascal's triangle. If this is the meat of the notes, guys, so you really want to hone in right here. If we are asked to find this expansion to the 4th power, then I'm going to go to the row of Pascal's triangle that has the binomial to the 4th power. And in the first row, I'm going to list those coefficients. 1, 4, 6, 4, 1. All right. Again, it's to the 4th power, so I know I'm going to have 5 terms. So you can see that my table actually has 6 columns. The first column is just for organizing stuff. I don't really even need to show that first column. But 1, 2, 3, 4, 5, because those are the columns for each individual term. All right, so this is the first term, and then second term, and then third term, 4th term, and 5th term. You need a column for each term that you would have. If I wasn't interested in the full expansion, I may not need to show every column. I'll show you that in the next. Any questions so far with how I've organized and broken this apart? This is your time to ask your questions. Looks like Catherine has joined us. I am recording this, by the way, so you're all good?
Yes.
Yep.
Good to know. All right. So, excuse me. Here we were asked to actually expand the whole binomial, right? Find the following expansion. So we actually we have to write out the full expansion like this was expanded, right? Full expansion. And it's going to have 5 terms because it's to the 4th power. All right, so in your first column, I've got coefficients are going to go across the first row. The expansion of the x term, the first term, is going to go across the second row. And the expansion of my third term, or sorry, my second term, which in this case is 3, is going to go across the third row. So put your Pascal's triangle values across the first row. Put the expansion of the first term, 2x. You know what? Let me color code this. Let's put the 2x across here, and let's put the 3 across here. All right, so what happens to the 2x's? According to our pattern, what should happen to this 2x as we go across here? The first term, it should be 2x to the what? Anyone? Crickets. Anyone? 2x raised to what power here?
1.
Not 1.
4.
Let's go back and look. Right, in our example here, the first term takes on the power of the expansion, which is 3 in this example, and then it decreases 2, 1, 0. But the second term starts at 0 power and then increases 1, 2, 3. So somebody said it, was it Chandler? This should be 2x to the 4th power. And the next one will be 2x to the, anyone?
3rd.
To the 3rd power, thank you. Yeah, you say that as if it should be obvious, but the truth is, it's clearly not obvious to everybody. All right, so this is 2x to the third. I'm going to rewrite this. This was 2x to the fourth, which, by the way, when you expand it, that's 16 to the fourth, x to the fourth, 16x to the fourth. And this one is 8x to the third. And then next we'd have 2x squared, which is 4x squared. And then we'd have 2x to the first power, which is just 2x. And then we'd have 2x to the 0 power, which is just 1. Now we do the same thing with the 3, except this time we increase. We start at 0 and we go up to 4. So it's 3 to the 0, which is 1, 3 to the first, which is 3, 3 squared, which is 9, 3 cubed, which is 27, and then 3 to the fourth, which is 81. Okay? Now to find each individual term, we will multiply vertically. So 1 times 16x to the fourth times 1. The first term is 16x to the fourth. 4 times 8 times 3. Well, actually, it's 4 times 8x cubed times 3 is 96x cubed. 6 times 4x squared times 9 is 216x squared. 4 times 2 times 27, or 2x times 27 is another 216, but this time it's just x. And then finally, 1 times 81 is 81. The expansion of 2x plus 3 to the fourth power is right there. 16x to the fourth plus 96x squared, x cubed plus 216x squared plus 216x plus 81 in descending order. Now, do you have to do it that way? No, not at all. If you wanted to, you could go 2x plus 3 times 2x plus 3 times 2x plus 3 times 2x plus 3. And you could take the time to multiply all 4 of these terms out and simplify, and you should get this. It'll come out the same. Same answer. But Pascal's triangle allows us to organize the information in pieces and then put all the pieces together as a final answer. Questions there at all? All right, we have 2 more examples, and they are a little quicker because we don't have to do the whole expansion here. In these examples, all we have to do is find the coefficient of one term. So notice the directions. It says find the coefficient of the y to the 5th term. And in this problem, not too hard yet, because they just gave us x and y, but they made it a little different. It's a negative. All right. So it is to the 7th power. 7th power here. So I would go up and I'd look at Pascal's triangle. Here's the 7th power. And the numbers there, blow it up a little bit, are 1, 7, 21, 35.
Can you scroll down a little bit, Mr. Heineman?
Scroll where?
Scroll down. We can't really. Oh, never mind. I understand what you're trying to do.
So I'm
Sorry.
just pulling the numbers here. 1, 7, 21, 35, 35, 21, 7, and 1. All right. So 35 is the biggest number. It is repeated twice. So 35, oops. 21, 7, 1. Right? So that's what it would look like. I don't know if I were doing this on my own, if I would even write all of them. because really they only wanted the coefficient of the y to the 5th term. And since y is my second value here, I need to be careful because it's negative y, it's not just y, and that negative is going to be important. So the first one would be negative y to the 0, and then this one would be negative y to the 1st, negative y to the 2nd, negative y to the 3rd, negative y to the 4th. This one is negative y to the 5th, right? So it's really just this one here, just this column that I care about, because this is where I would have the negative y to the 5th power. All right? It only asks for the coefficient of the y to the 5th. So I only need the number that would be in front of this term here. I don't have to fill in the rest of this chart. It is important, though, that you recognize we did have x, and this would be x to the 7th, 6th, 5th, 4th, 3rd, 2nd. So there's technically an x squared here, but there's no number there. So even if you left this x squared off, it's not going to affect this at all. Can anybody tell me what the coefficient is on this term? We're using this information. What is the coefficient on the y to the 5th term?
21.
Close. Try again.
Oh, yeah.
What's happening here?
Correct.
Is it negative 21?
Negative, right? Because this is negative 1 to the 5th. And so it's going to leave a negative on this term. This term turns into negative 21 x squared y to the 5th. And so they want is negative 21. Only the coefficients, not the whole term. This is clear. This is something you got to be real careful of, because in my math lab, if they ask for the coefficient and you give negative 21 x squared y to the 5th, you're going to get it wrong. They only wanted the coefficient. So I'm only boxing negative 21. I don't want you to do all the work right, but then enter the wrong answer because you didn't quite understand what they were asking for. They asked for just the number, the negative 21. Any questions there? All right, one more.
Wait, I have a question. So we don't multiply 20, like we don't square 21,
No.
or no, okay.
Numbers from Pascal's triangle are exactly as they are presented in the triangle. We're not changing those at all.
Okay. So if x was like, to begin with our original binomial, if it was like x squared minus y to the 7th power, then you would square whatever the...
Yeah, it would just be the x squared would start out as, really, I would guess it would be x to the 14th, and it would slowly go down, right? It'd be x to the 14th, x to the 12th, because it would have to, it would be, if this had been squared to begin with, then this would be x squared to the 7th, and then x squared to the 6th, and then x squared to the 5th, and so on.
Okay, so then we don't mess with Pascal's numbers. They just multiply. Okay.
They multiply by whatever comes out in these other two rows.
Okay,
Those
thank you.
stay those numbers. You're not going to mess with them until you're ready to kind of write your final term. Then you'll multiply them by whatever numbers show up in these two. All right, good question. Anything else? Okay. Last example then, and I've already drawn a table. I didn't create this table entirely. I just, the first couple of terms, because this one asks for, if I just follow what it says, the coefficient of the x to the 7th term. Okay, well, it's x and 4. And so I won't fill in Pascal's triangle yet. We'll do that in a second. But this is going to start out, since this is to the 9th power, it'll be x to the 9th, x to the 8th, x to the 7th, x to the 6th, right? And they only want the x to the 7th, so I only care about this column, all right? I don't need everything else filled in. This would be 4 to the 0, 4 to the 1. This would be what? What goes in here?
4 squared.
4 squared. Good. So it's 4 squared. Again, that's because this is 4 to the 0, 4 to the 1. This would be 4 cubed. And then it would go all the way up until I get to 4 to the 9th power at the very end. But I only want this term, and I want the number in front of the term. All right, so now we got to go get those Pascal triangle numbers. The reason why I held this to last is because we don't actually have that expansion. Our numbers went through 7. We don't have to the 9th. And so if you're doing a MyMathLab question, it asks for the 19th expansion. You want the numbers from the 19th. You're going to have to look that up, or you're going to have to create. When I say look it up, I mean go to Google and Google Pascal's triangle and try to find a longer expansion, because I've only given you one through the 7th row. All right. So you can either do that, look it up, or you could just keep writing it out on your own here. I have more room up here, so I'll do it here. So if I was, this is the 7th here. So if I was doing the 8th, it would be 1. I add, so 8, 29, what's that, 56, 70, 56, 20, that should be 28, not 29. 28, and then 8, and then 1 again. That's the 8th row. All right, and then the 9th row would be 1, 9, 36, what's that, 70, 84, and then 126, 126 again, 84, 36, 9, and then a 1 on the end. So this purple row is what we want for the problem we're working in. All right, so I'm going to refer back to that. So now this is the expansion through the 9th row, x plus y to the 9th power. So come back to this. Sorry, they start out 1, 9, 36, 84. So 1, 9, 36, 84. The 36 is the number I was looking for. All right. Okay, so answer the question for me then. If that number is 36, then what is the coefficient of the x to the 7th term of this binomial expansion? Anyone? You can grab a calculator if you have to. What would you do? What do you have to do in order to find this coefficient?
Is it 576?
It is 576. 576 x to the 7th power is what this term turns into when you multiply all those values vertically. The number we want is 576. 36 times 4 squared. Very good. All right. Okay, I want to make one final comment, and that is I'm going to stop sharing this screen and I'm going to share my computer screen instead. I'm still recording this though, so it's still going to be on the recording. The comment is about MyMathLab. Sorry, I didn't mean to show all that, but hopefully you didn't see it anyway. It's going pretty quickly. You guys, oh, you're not, I didn't share the screen yet, so you're not seeing it. Hold on one second. Let me pull up MyMathLab. And then I will share this screen. Come on. There we go. This is key. You guys are going to want to know, pay attention to this. If you are not listening or not focused on, oh, dang on it. I'm supposed to be sharing that screen. All right, you guys seeing this right now? MyMathLab in front of you? Okay.
Yeah.
MyMathLab is just 5 questions. Now this one actually wants you to expand the whole thing. So you'd have to actually give, like we did in the first example here, you'd have to actually, x cubed plus what. Anyway, this one's an actual expansion, but notice the directions here. Binomial theorem. I didn't say anything about binomial theorem. We're not doing binomial theorem. it says use the binomial theorem to expand. I'm telling you, use where it says binomial theorem, use Pascal's triangle to expand. So replace binomial theorem with Pascal's triangle when you read this. Anywhere where you see that it says binomial theorem, instead use Pascal's triangle. If you go to the question help and you view an example, it's going to show you stuff that we did not talk about. You guys see this? It's got n over 0 in this big parentheses, n over 1, n over 2. That's actually combinatorics. That's a combination. Section 10.5 uses stuff from 10.4. Binomial theorem was 10.4. We didn't study that. But you can do these with Pascal's triangle, which we just studied. So instead, I'm going to say, replace binomial theorem with Pascal's triangle when you read this, and do not do the view an example. It won't help you. Okay? Any questions with that at all? I'm unsharing my screen, and I will stop the recording